Thank you for inviting me to this meeting. When Evan first called me up, actually I had no idea that there was that much interest in nanomaterials classification, and certainly I was surprised there was that much interest in nanomaterials classification that I didn't know about. So I want to talk a little bit about, just tell you a little bit about my background, because my talk is going to be, and I'm going to do that in two parts. So my talk is going to be about scientific discovery in the information era and databases in general. And then I'm going to switch over to classification and work that we've been doing on the classification of nanomaterials. So I'll introduce myself in that context when I get to that point. But let me just give you a little bit of background about why I'm even got interested in scientific discovery and databases. I got a PhD in chemical physics, computational chemistry really, and at the time I got out, many decades ago, there were no jobs in that area. So I got a job, a postdoc at a place called JILA, the Joint Institute for Laboratory Astrophysics in Boulder, in a scientific data center. And we collected data on atomic and molecular collisions with atoms and molecules and electrons colliding. And my first assignment was to write a database management system. And on the way over here, I told people about, we had a much better system than Oracle or anything else. We just didn't have the entrepreneur spirit. So, that's why I'm here and not sailing with Larry Ellison. Okay. So, but then I bounced around and I ended up at NIST, and they wanted me to start a program on scientific data for material science. Now, at the time, it was National Bureau of Standards, and they run the Standard Reference Data Program. And how many people have ever heard of the Standard Reference Data Program at NIST? One. Okay, two. All right, well, it is the largest and most comprehensive program for producing high-quality scientific data in the world. And the real focus of the program is the collection, evaluation, and dissemination of scientific data. And they do it in physics, chemistry, materials, lots of different areas. NIST has the only copyright authority within the US government. So when that's one reason they hired me, because I knew about databases. When computerization of data became prominent in the 1980s, we started building personal computer databases that we sold in thermochemistry, atomic physics, many areas, phase diagrams. And then when the internet era came about in the 1990s, NIST created, I think before I left in 2004, we had created 25 online comprehensive systems of all sorts of databases in chemistry, physics, and what have you. So I have a long background in scientific data, materials data, and things like that. So let me just get started now. And what I'm going to talk about today, if I do this correctly, well, that's not the right way. Okay, I'm going to talk about four things: the data revolution in scientific discovery, some information about science today, which we all know about, but is worthwhile thinking about, and then what I call the tyranny of independent variables, which is really, to my mind, the foundation of categorization, and then talk about work we've done on categorization in nanomaterials. And so this doesn't exactly follow my abstract, but as I saw what the program was about, I decided to talk a little bit more about what we're doing actually with respect to the categorization of nanomaterials. Then I have some closing remarks, and depending on time and interest, at some point I want to raise this question about whether categorization is a risk activity or a knowledge activity, or maybe it's both. So let me just get started about my first thesis, which is that scientific discovery really has changed in the... Okay, all right. Scientific discovery has really changed. The paradigm has really changed in the information era. And I've talked about this a great deal all over the world, and it's interesting to see what kind of reaction we get to this. But if you just look historically, the collections were managed by a small number of people. You could read the collections, you could interpret them, and then one person or a small group of people could actually then make some kind of scientific discovery. But today, collections are managed by groups. The collections, when they're terabytes or they're federated systems with 50 different databases, are not readable by any individual. They're really interpretable only by software. What I mean by that is analytical software, visualization software, spreadsheets, what have you. And then the question one has to ask itself is that, are the discoveries in the future really going to be made by people or computers or a combination of both? And I would argue in other situations, I would expand on this, that the discoveries are more or less going to be made by computers, and the role of people will be verification. But we're not going to go there today. There are too many philosophers in the room for that. So what I'd like to just give you a little bit of my perspective of the history of databases in science. And the first three goals of making databases were very, very simple. You want accuracy. You want to be able to store a number accurately. The second is that you want to have a lot of numbers that you know about, and you want to store them just in case you don't remember them all. And then third, once you started doing that, you want to start systematizing them. So let me give you what I consider to be some of the earliest examples of each of these things, with some apologies to the Chinese. But the first database that I've really discovered is in Newgrange, Ireland. It's a mammoth structure. I've been there several times, and the temperature has never been above 40 degrees, and the wind velocity has never been below 40 miles an hour. So, dress warmly if you go there. But it's about 5 acres, and it stores one data point. And that data point is on winter solstice. It shines down this entrance here onto a little altar. And on December 21st, 2000, you had to sign up about 3 years in advance to be able to go in there. It is a cult place of the highest order. But it's 6,000 years old, and it stored one piece of data. If you go a little bit further and you want to store several observations, I show Stonehenge here, but throughout the Celtic region in northern France, in western Belgium, and in Great Britain, there are many, many sites that store the position of moon and stars at various times, and they actually stored several observations. There probably were easier ways to write them down, so obviously these databases had other applications besides just the storage. But in essence, these are the way that people stored information many, many millennia ago. Then we started getting to more comprehensive databases. This happens to be an Arabic copy from 800, but it's of Galen, who is one of the very first person to write down the functionality of different botanical and animal species. And he was not the only Greek to do this, and there were early Romans who did this also. And then Pliny the Elder is one of the very first to put together an encyclopedia where he tried to systematize the data, tried to create some kind of category to make sense of it. I don't know the extent of this copy, but I don't think it had the Microsoft symbols on up there to begin with. So the idea that I'm trying to convey here is that the idea of storing scientific knowledge in a permanent way that you can use for applications aside from just storing that data has been with us for a long, long time. So let's not think that just because we're in the information era and we have, databases on our PC, that we've come up with this idea that you need to be able to preserve the information first for your own use and your own application, but to pass on to other people. So, following the Baconian revolution, databases also changed character and served a different function besides just simply storing them, preserving them, and the kind of systemization and categorization that people were doing, creating encyclopedias. As I've shown here with these four things: extraction, explanation of the complex, prediction, and physical theory from data. And I'll give, excuse me, I'll give you simple examples. It's generally conceded, though not necessarily true, that Tycho Brahe was the first one to really assemble a lot of databases that people could exploit to discover really important new physical relationships. And as you know, Kepler and others spent a lot of time working with this data to trying to understand the relationships between what it was measuring, in this case, the motion of various planetary objects. But then you get more complicated, where you needed information from several disciplines at once, and drawing on the pseudo databases that people put together, the compilations in geology and botany and zoology, as well as the personal observations that Charles Wallace and Alfred Wallace Stevens had made, to come together with an explanation of many different observations from many different types of people over many periods of time, to explain something that really, the idea of evolution, of course, was there, but assembling the facts to talk about the origin of species and the evolution of a species really was one of the first examples of building on multi-dimensional databases to come up with some new scientific knowledge. Predicting the new phenomena, I like to use the example of Mendeleev's periodic table. And if you go to the original literature, his table is not very pretty and doesn't reproduce well, so I use one from NIST. But what he was really able to do was, by assembling these data into a coherent collection, was then to predict the existence and properties of elements that had not been discovered. And this is really, in the history of science, I think, a very amazing step forward to predict something that you don't know exists, but you said it should exist, and this is how you find it because it has this properties. And that is a really major step forward. Then the last example I want to put together is from the physical sciences, is the explanation or the advancement of a physical theory from data. In this case, it turns out to be a very, very small amount of data that led to the first understanding that the physical world was not continuous. Balmer and Paschen and others who measured these spectroscopic lines could only explain them by these very complicated mathematical formulas that eventually Max Planck and others realized predicted discontinuity in physical matter. And eventually that led to the development of Niels Bohr and Aaron Schrodinger, my heroes, but it's interesting, and in some other talks I talk about this, that if you had all the spectral data in the world together, could you have predicted quantum mechanics? And the answer is probably not. But there's a chain from the collection of these important data that were done very, very, very accurately, and then analyzed very carefully, and then producing results from the analysis that challenged current physical thinking that eventually led to the development of the idea of quantization and then how that is expressed as a physical theory. So what I've done is kind of sweep through the first 6,000 years of databases, and then we came across the computer era, and nowadays the history is just cascading. The first two databases were in crystallography and neutron data, and there's very specific reasons why they were done, and they weren't real scientific reasons. They weren't trying to preserve the data. For crystallography, you couldn't deconvolute the diffraction patterns without very advanced software, and people realized that, well, you know, this software is generating data, is on the computers, we may as well do it. And people during the 1950s and 60s at Cambridge and in the United States, and Olga Kennard and others created the first crystallographic major databases, and these databases are extremely large now. In neutron data, it came out of Atoms for Peace in 1956. The first effective data exchange format in science is X4, the exchange of neutron data, and it was established by scientific treaty. So those of you who are trying to build standards for data exchange, you might think about contacting your ambassadors. But then in analytical chemistry, and because of environmental and toxicology, databases became in. The first comprehensive federated system of databases was the Chemical Information System that was developed by Steve Heller, Bill Milne, and the third person whose name I forget, mass spectroscopist at NIH, I apologize to him. But they built, that was a very comprehensive system. And then, of course, space science and large physics experiments had to collect their data because electronically they had no other way of doing it. And then through the last 2 decades of the 20th century, other areas moved into that. And today, of course, every area of science has very large databases. They cover an incredible array of objects and an incredible array of data. And there's some interesting facts I put on there on the right that really emphasize what very large mean. So I just want to quickly go through a few things about science today, just to refresh your memory that science itself has changed, but the basic goals have not. The 2 basic goals of science have been, certainly since the Baconian Revolution, but even prior to that, first is our thirst to understand how the world works. But then there's been the second, and in some ways, a major driving force in science, especially in the last 300 years, and that is much science is based on the fact that we are developing technology and we want to understand it so we can make that technology we're inventing better. Maybe today science is operating in the reverse, and that's more important than the understanding of the world. I think it depends upon the amount of wine you have when you figure out that order. But there's another change in science today that affects scientific discovery and also is very pertinent to the question at hand about categorization and nanomaterials, that we really move from the equal MC squared to understanding the human genome. Okay, we've really gone from reductionism to constructionism. Rather than looking at physical phenomena at the most fundamental level and trying to understand the basic laws of motion, basic laws of chemistry, we're trying to understand, put all that knowledge together to predict behavior of real systems, the atmosphere, the environment, and human beings and other living matters, as well as the universe itself. So these are fundamental changes, and in our perspective of doing science over the last few hundred years, But on top of that, we've added e-science. And I won't go over these things, you know them very, very well. Everybody's computerized, everything is being captured, and the tools we have to do this e-science are readily available to everybody. That has a lot of impact on generating scientific data. I put 4 of the major ways that we generate scientific data. The 5th one, surveys, I have not included. But in big science and small science, people you can generate large and small amounts of data, but more importantly, that they're facing these questions of what independent variables do you have to worry about when you collect these data. So just to summarize this section about today's science and e-science is obviously science today is more fully based on data and data collections than ever before. But there's a small punchline, oops, and that has to do with there's a difference between measurement and property. And I'm going to get back to this several times, but we make measurements every day in science through experiments, through observations, through calculations, through testing, but we have to understand that a single measurement is not necessarily a property of the system. That measurements are really a one-time look at nature, and properties are the inherent characteristics of nature itself. And if you look back at the history of generating property data in chemistry and physics and astronomy, the most mature sciences, that it takes decades. In thermochemistry, it took almost a century, from the 1870s to the 1970s, to routinely measure enthalpies, heats of formation, and something like that accurately so that the next measurement could be considered a property of the system. Same thing for atomic spectroscopy. Now we're looking at measurements on very complex systems such as nanomaterials, et cetera, and one of the questions you can ask yourself is, not only don't we have adequate collections of nanomaterial measurements, which we don't have adequate collections of nanomaterial property data. And I think there's a lot of implications for that, especially for the discussion of this workshop. So now I'd just very briefly like to remind you of the tyranny independent variables. So I just going to do this in the context of 2 things. There are many more problems associated with it, but I'm just going to talk a little bit about too much data in complex systems. And the challenge is, first, with too much data is just the bottom 2 points. You know, how do you know when you have a large amount of data that you have a good quality data? And then second, which data are important? And if you start thinking about this, you know, first, bad data quality leads to bad science and bad decisions based on that science. So data quality is not something that we can ignore, because if we're going to do things like issue regulations, for example, on nanomaterials, but we don't have good nanomaterials data, that's making decisions based on bad data. And if you start looking at large data collections, like a terabyte of data, what does data quality mean? How do you ascertain the quality of an individual data point, or all the way down to the entire collection? So when you have a lot of data that has a lot of variables to it, then the second aspect of it is, how do you know what's important? How do you abstract the important features? And I just show some numbers on the left here to show that, you know, if we talk about cellular interactions with something, you know, there are 80 trillion cells in the body, and we can categorize them into different types, but they have a lot of different types of interactions, even with the same material. And truly great science is having insight as to what's important, but if we're using software to help us in the discovery, how do we actually teach that software how to figure out what's important? when you start talking about complex systems, there's a number of things you can talk about, but I just have time to focus on independent variables. And the example I'm going to use is simply brain imaging, where people are now collecting these things, and they're doing this as you stimulate the brain. They're using different technologies. They're using different kinds of stimulus, pain, visualization, auditory, tactile, and others. And the details have to be defined and recorded. But if you look at a person and you say, well, what were the things within that development of that person, of that brain, that actually resulted in that particular interaction, it becomes very, very difficult. Another example I often use is obesity. You know, people consume food their entire life. How do you understand which consumption at what point and which physiological reaction to what you consume actually is the cause and effect that affects this very complicated behavior? So when you talk about what are the most important independent variables for recording brain history, that obviously is still a question, and in many other areas of complex science, that's the situation. I can't do a talk without one equation. Your properties are a function of n independent variables, and if you don't know what n is when it's large or unknown, it's very, very tough to figure out what properties really are dependent on which independent variables. And now I'm going to talk about this in the context of categorization and nanomaterials. So I'll put up the, oops, I won't put up the next slide. Okay, so in 2011, some people involved in ISO Committee 229 on nanotechnology and the OECD Working Party on manufacturing nanomaterials approached an organization called ICSU, the International Council of Science. And I don't know if any of you know ICSU, but ICSU members are National Academies of Sciences and international scientific unions like International Union for Applied Chemistry and many other international unions. And they said that the scientific basis for some of the standards that are being developed was not adequate, and could ICSU put together an effort to try to bring together on a multidisciplinary level a group of scientists to help improve the scientific base of some of the standards that are being put together. Well, CODATA, which some of you have heard of, is the data organization under ICSU, and ICSU knew me, and I used to be president of CODATA, and people knew my background in data science and informatics and materials data, and they asked me to put together an effort to address this question of how to improve some of the quality for nanomaterials information. So I just want to tell you about that adventure. But here's the punchline. That obviously, you know, categorization is based on important properties and properties of function-independent variables, and therefore categorization is based on important independent variables, and when you don't know which independent variables are important, how do you categorize? And this guided our thinking within the effort, because the question I started asking is what kind of data do you have? How do you characterize it with respect to its independent variables? And do you know which ones are important? So I'm going to quickly run through these, you know, why is it important, what are the goals, what we're doing, and what the outcomes are going to be. So clearly, when you want to categorize nanomaterials, the first three things that pop up is, you know, reducing testing, predicting properties, optimizing those properties, and all that can help facilitate regulation. But there's also other reasons to categorize, and that's to provide guidance in identifying new materials, figuring out what's really important, figuring out how to measure what cannot be actually measured now, and there's some major issues with respect to that, as I'll point out. I'm sorry, we'll get that. And then finally, demonstrating our knowledge by controlling those independent variables and getting predictive results. So our goals in doing this work is that we wanted to make sure that we were looking at things where cause and effect was really taken into consideration, that we understood the science, and that we could demonstrate that understanding by doing experiments that controlled the important independent variables and predicting the results. So we put together an international working group under CODATA, which is the full name is Committee on Data, Science and Technology of the International Council of Science, and VAMIS, which is a pre-standardization materials testing international organization. We had representatives from over 13 different disciplines, everything from food science and technology, nutrition, to material science, to experimental measurement, engineering, medicine, chemistry, physics, what have you. We've had many workshops in the US, Asia, and Europe. I don't know whether that July 16 is still there. That was the last one we had. It should have been 215. Anyway, and we had a version that was released on what is called the Uniform Description System for Nanomaterials in February. We've made detailed comparison with other ways of people looking at it, and I literally just completed the second revision, and that's just started review. But let me talk about it in some kind of detail, what we were trying to do. This is our basic data model that you have, and to my mind, this is a basic model for all scientific data when you're trying to model it. You have an object or material, and it has properties under certain measurement conditions, okay? And what we have done is focus on this, to be able to describe nanomaterials accurately. And the goal was very simple: uniqueness, that we would be able, our system would be able to differentiate between every other nanomaterial. So when we're talking about nanomaterial, people know exactly which one we're talking about. And second, equivalency, that if you have two different people studying nanomaterial, that you could compare them and say they are the same nanomaterial to the degree that you want them to be, and then you can combine their data sets. So, how did we do this? Well, first thing we did was a big survey, and we looked at this, and I've been modeling data for a long period of time. And these are some of the issues on the left. It's very complex information. There's a lot of areas where we don't have knowledge, and I'll point some of those things out. What's interesting is there are no comprehensive collections of these data, which makes it difficult to test some of it. It's very multidisciplinary. There are many user communities, and there's a lot of premature standardization going on. And the consequences of each of those things, obviously, are given on the right. But this was our approach. We used natural language, meaning English language, technical language. We did not use ontology. I don't allow the word ontology even to use, in the thing, even though I've developed many ontologies. We wanted to be understandable by researchers and users of nanomaterials across a diversity of areas. So during our review, we've had people from all these different disciplines come in, and they actually can understand what we're trying to do. We've broken it up and say, what are the basic information categories we use to describe nanomaterials? Then under those categories, what are the detailed descriptors? And we tried to be very systematic, and let me back into that just for a minute. That when we were working on materials databases, and we built a very large-scale, what's called the National Material Property Data Network in the United States, pre-internet, we had a standards committee under ASTM that developed standards for describing materials and describing testing the materials and exchanging data. And we had developed some insights as to how you approach describing a material as opposed to chemicals. Even our committee also did chemicals, but I'm talking about engineering materials. So we could build on that experience. And let me just back up. So we had a lot of experience about how you go about this systematically, and I'll describe some of those things. Now, the first thing is, we said, and this was quite controversial and generated a lot of discussion, is what do you mean by nanomaterial? So we ended up defining 4 types of nanomaterials. The first type is an individual nano object. And I can assure you that we ended up choosing that term, I ended up choosing that term, because it offended everybody. Okay, it was universal offensiveness. It's not nanoparticle, not nanomaterial, it is an individual nano object. And just as like in chemistry, where you have to describe the atoms that go into molecules, I said we need to have understanding of the basic unit of a nanomaterial. Second, you can have collections of that, and in reality, those collections are really important. Third, you can have nano objects in bulk material. And then fourth, you can have bulk materials with nanoscale features. And now, how do you describe each of those things? Now, this is not just, I was going to say philosophical exercise, but this is not just an intellectual exercise, because the ISO definition of a nanomaterial is here. It is a material with an external dimension, 1 to 100 nanometers, or having an internal surface structure in a nanoscale. And that emphasizes the individual, the aspects of an individual nanomaterial. Okay, the definition is almost equivalent. This is the definition, the ISO definition of a nano object, which is almost the same as that. So, okay. Now, and feel free to interrupt or challenge. And then that's the individual, that led to how we're going to do with individual nanomaterials. But the EU definition, what?
I'll take you up on that. So that means that most chemicals that we know about today that are of reasonable size are considered to be nanoparticles.
Most chemicals are not that size. DNA, large biomolecules are, and large polymers are, but most chemicals are smaller than 1 nano. They're probably about 0.5, 0.6 nanometers.
When you consider some of the larger entities that we know of, that their full chemical structure, there's quite a number of them that would fit that criteria.
Well, that's the case. Okay. Well, you take a carbon nanotube. Okay, is that a molecule? And certainly, that would be on that scale. So, yes, it's possible for a large molecule to be on the nanoscale and could be classified as a nanoscale. Yeah, graphene's remember, it's you can have sheets of graphene which are bigger than nanoscale, and you can have some that are smaller. So, okay, so that covers. So dealing with the individual, I'm not dismissive of your question. There's a lot of, if you notice what the definition is approximately. So, because that drives the regulators crazy, absolutely crazy. So then that covers, oops, I'm going the wrong direction, excuse me. That covers, why we were looking at the individual nano objects, but then second, the collection, well, this is the EU definition, okay, and it talks about could be unbound state, aggregate, or where 50% or more of the particles in the number size distribution are in the nano scale range. There isn't any approximately with this, but there's some weasel words about this, because down here they say, well, it could be replaced by some other threshold. And the reason they picked 50% was literally political, because they wanted 20%, I think, initially, and scientists fought it, and anyway. But the point here is that the EU definition of nanomaterial doesn't talk about one individual nano object, it talks about a collection. So we had to figure out how to describe both of them. So that's why we have that. For nano objects and bulk materials, basically said, well, they're either individual or collections, and you can use the tools that we developed to do that, and we didn't really talk about nano bulk materials and nanoscale features. So what are the categories? Now I'm going to just talk about nano objects. What are the categories of information? We broke them up into 4 major areas, what we call characteristics, production, specifications, and general identifiers. And they include the things that you probably would think about: shape, size, chemical composition, physical structure, crystallographic structure, surface description, and then a whole bunch of stuff about production and the specifications and general identifiers. And in this and other places, I have this asterisk where we have a really fairly good idea of how to describe shape and size and chemical composition, but honestly, people are whistling Dixie when it comes to surface description, and I'll talk about that a little bit more. So, you know, this is sort of the diagram of it, that you have a nano object and all these different things have different types of information categories, but to go into more detail, the characterization for chemical composition, you can describe it on an atomic composition level, a molecular composition level, the chemical moiety level. Crystallographic includes physical structure and unit cell. The shape includes shape type, shape features. Physical structure gets a little more complicated because you can have structured and unstructured things, and then you can have different types of structures: shell, layer. You can have additions and entrapment. If you're interested, you can just go to the website, or I can show you. Then we have tables. For each of these things, we have tables of the detailed descriptors that are needed for that, and definitions and examples of them. That's what the revision really did, was add a lot more clarity to the definitions. Now, how do you describe a collection of nano objects? And it's different information. In addition to general features, you have the composition, size distribution, physical structure, interfaces, association, agglomeration, aggregation, surface description, stability, and topology. We've had a lot of debate about stability and topology, whether stability is some kind of property that you measure, or is it inherent to characteristics. So under stability, we only deal with what I call uninitiated instability events. It decomposes or is shipped or something like that. And topology, I mean, obviously you need some quantitative description of them, and right now people talk about the topology and morphology of nano objects and collections of nano objects, but there is no real good quantitative description of them. So this is available. It's available under a Creative Commons license, and we hope that over the next 6 months it's going to be reviewed intensively. Hopefully there'll be just a few changes, and then most likely it'll be submitted to ASTM Committee 56 on Nanotechnology for them to advance as a standard where there'll be more systematic review of it. So,
can you say more about what you mean by? Can you say more what you mean by topology?
Topology is two things: the general, the relationship of one part of a surface to another. Okay, so the famous teacup goes into a donut kind of thing, and then the second is the relationship of the functionality of one place on the surface with another place on the surface with this connectedness. So some people have tried to use graph theory to connect. For example, if you have a star shape nano object, and you want to connect the reactivity at a point of the star with reactivity at the angle of the star, you know, how would you describe that? Okay, how would you say they're connected, and how you would describe that?
So I guess I'm confused about whether topology attaches to objects or attaches to collections. And I mean, this might be because I hang out with...
Because you could talk about potentially the topology, say, of an individual carbon nanotube, but so far we've decided it only applies to a collection of these things.
Mm-hmm.
So you'll get a copy. You can
Yeah.
review it and comment, and you know.
I guess I mean I have a colloid bias, obviously.
Yeah.
And I don't really understand how you would describe the topology of this, for instance, right?
Well, you these information categories and the descriptors therein are not mandatory for every nanomaterial. Every nanomaterial, you will pick and choose what you need to do. But for example, size distribution is very important on that. And as you well know, or maybe you don't know, that the determination of size distribution is in a lot of turmoil right now, because no experimental method covers the full range from 100 to 1 to 100 on all three dimensions. So you have many different ones, and this is a big problem in showing compliance with the EU, because if Group A uses this method, Group B uses that method, they don't necessarily overlap. And groups like REACH, which is sort of the Scientific Committee on Chemicals and Commerce of the EU, I think I got that right, is, you say, well, they're in charge of regulating chemicals in the EU, and those, how do you actually force people to use a method that isn't 100%? You were going to ask something?
Let's finish your thought. I'm still thinking of my question. Go ahead.
Okay, I'm finished.
Oh, okay. So, how much of this is reflected in the definition? I'm thinking of how you regulate things like this, because I've been in discussions about how to regulate nano objects or nanomaterials.
Yes.
And there's a ton of focus on size.
Yeah.
As a determinant.
Right.
Almost, everyone does.
Can I get back to that point?
Sure.
I'm going to get to that, I think, in one more slide. And I'm sorry, I'm slightly hard of hearing. That's why I have to walk up. Let me just go back to this question: what is a nanomaterial? Why we're doing this? Because when you collect data on the nanomaterial, you really want to know exactly which nanomaterial is being considered, and then when we want to test it, if we have this information, then we could relate the result of a test to a specific feature in the nanomaterials. And now that raises a question of which nanomaterial is being tested. And I have a series of slides I'm going to run through very quickly by saying, this is a normal sequence of events in testing the nanomaterial. You get it? I don't know, is there a pointer here? Yeah. This way. Okay. All right. So anyway, you can read. Upper left, you get it. You buy it, it's made naturally, what have you. And then you receive it, and it's been shipped. You stored it, it aggregates. The jerk put the temperature up to 100 degrees in the storeroom or something like that. Happens all the time. And then you prepare for testing, and so you kind of try to reverse the effects and get it back into the state when it was manufactured or natural, and you don't. And then you sample what you've prepared, and then you put it in the test environment, which immediately has some kind of media that puts a corona on it or pH, what have you. So what you try to do is to say, okay, given all this stuff, is, you know, if we say, here's a test result, how do I ascribe it with, you know, a cause and effect to, you know, which thing along here, and to do this? And we're not being as careful right now in doing this as we could. Okay, so yeah, this just kind of summarizes, you know, that you have a different nanomaterial. You could describe the take the description and say, well, here's as manufactured, and now each one of those steps is kind of a post-production step, or you can describe the nanomaterial as you go along. And you just, one point I tried to make is that the present ontologies and data models for describing toxicological experiment mixes a lot of this stuff together, and it's very, very hard to sort out the cause and effects of it. Okay, this is not a moot conversation because the regulations are being passed. France now, you have to label nanomaterials in food. Nobody knows why, but they do it. But if we don't know which nanomaterial, which feature causes effect, we actually are in, you know, have some big problems with respect to that. So can nanomaterials be classified by certain features? And you guys are all experts in classification, so I really won't go into that in any detail. But suggestions already include size, shape, surface characteristics, zeta potentials, and more. So let me just pick one of them, zeta potential. And Greg Lowry at Carnegie Mellon, there's a group under NIH that has teleconferences every week. Is run by the National Cancer Institute nanotechnology group, and it's essentially the nanoinformatics people active in the United States with a few from Europe. And we've written a series of papers about various aspects. And Greg Lowry just finished one on the detailed analysis of zeta potential and IEPs. And I've been criticized for being negative, so I'm making this positive. There are many opportunities for improvement. But here's kind of the punchline, and this is where I really pushed it. The EPA says that, you know, when you change a form of a nanomaterial and the zeta potential changes by so much, then by more than 5 standard deviation units, is now a new nanomaterial. You have to do new testing. Okay, but we've shown that zeta potentials can range by a factor of 10 to the third, 10 to the fourth, depending upon how they're measured and how careful you are in having, you know, impurities or pH control and things like that. So now that gets to your question. That's just for zeta potential, but you can do almost the same thing for chemical composition. There's a US Canadian group which rises and falls on chemical composition is the only way to classify nanomaterials. Shape and size, I have in my backpack an article by this group, the University College Dublin, that has come up with new ways to analyze the shape and is proposing that's a different way of looking at shape. Let me just switch now. That in addition to work on CODATA, CODATA is a partner with his EU Future Nano Needs, is led by University College Dublin, and one of its work items is to produce a system on categorization. I'm kind of in charge of that. That's why I was very excited to come here and find out what other people are doing. But here's some of the conclusions we've already reached. First, multiple approaches are possible, and that the classification must be on a few features or a small number of well-defined properties, and I put the word properties in there very deliberately. And then you must be able to show quantitatively and reproducibly that there is a relationship between these features and the property. One of the things in doing this work, I don't know if anybody is familiar with this work by Austin Hill, which talks about environment and disease, association, causation, and he's put together 9 criteria for differentiating between causality and association. I just put 5 of them, most important from my perspective, that strength, consistency, specificity, biological gradient, and plausibility. And as you begin to apply those to some of the systems that have been proposed for categorization, it makes you wonder. Again, trying to put that in a positive light. One of our goals of this is to recognize, especially this life cycle. One of the things that this group at UC Dublin has found out that there's a lot of biological crap that floats around in laboratories, and it's very, very hard to get nanomaterials for testing that's free of this crap. You know, pieces of enzymes and peptides and other biomolecules that are just going around, and to clean this stuff off and then be able to produce predictable coronas has proved to be extremely difficult. And that's, of course, because of the surface reactivity, which is I think, and Kenneth Dawson and others there think are underestimated. I just have a couple more slides. There's going to be an international conference on categorization that's being organized right now. I'm helping to lead that organization. It'll be in late 2016, 2017. And the goal is to help develop an international consensus, though this is my real goal, which is to help set up a roadmap to get a better scientific consensus. And there'll certainly be opportunity for everybody in this room to participate. We're trying to hold it at someplace nice. There was a quality nano workshop this summer in Crete, and that was last summer, which was very nice. And they've extended an invitation to us, but it's hard sometimes for US people, I mean, people on the West Coast to go all the way to Crete, you know, but it's worth it. Just end up, I always like this statement from William Bragg that, you know, sometimes science is not so much getting the new facts, but really thinking about them differently. And to my mind, you know, that's what understanding is really about. And to my mind, that's what data collections really help us facilitate, by assembling the facts that we can really do some good science on. So here are my final thoughts. Nanomaterials data are missing. I don't know how many of you are familiar with the nanomaterial registry that's run by RTI. It is now moving to University of North Carolina. But in their final presentation, which was just this last week, they talked about the last year they have added no data because they have been emphasizing, you know, reaching out to the community on better ways to get data. eNanoMapper, which is the most advanced database system in Europe, has virtually no data to test. And the big European programs, the Nano Safety Cluster and I forget, the Nano Registry Consortium, they are, they are generating data, but their database efforts are just, they're struggling with them, and it's causing them incredible agony. So that's a major issue, that if you're going to have categorization schemes, you need databases to test it against, and we simply don't have the databases. Okay, and then we do need more consensus. We need more discussion. The goals need more precision. And I want to point out, this is the first talk of this workshop, so at the end I might have entirely different views, but because of all the great work everybody else here is doing that I'm not aware of. I just point that out. I just wanted to point out one other thing, make one other comment, that on Thursday and Friday of this week, the NNCO, the National Nanotechnology Coordinating Office, is holding a strategic planning meeting in Washington that I'm attending. And I do have one goal for that, which is that I really want them to institute a better mechanism of communication of all the efforts that are going on with respect to nanoinformatics, of which I consider the categorization to be part of. I think there's too many activities that are going on, as indicated like in this room, that people just don't know about, and you probably don't know about, you probably didn't know what was going on in the future nano needs or even what CODATA was doing and things like that. And the only way we're going to make real progress on this is to have better communication. So I'm pushing very strongly with them to figure out a way to circulate, and probably none of you know what ISO 229 is doing, because I can't even figure that out. So I'll stop there. I had this one last slide about the potential for discussing categorization and risk of knowledge, but I think that will just come up because I've used up my hour, and I'll be glad to take any questions. Yeah.
Since you're trying not to be too negative, maybe somebody else can do it.
Okay.
But you described a really complicated problem in nanomaterials, but I think the situation is even worse in other areas, like brain imaging, for instance, and it's kind of related to the causation issue you brought up, but for philosophers, I guess it's also related to the problem that identifying kinds is really related to the problem of induction. So in brain imaging, it's really hard to guarantee getting more of the same when you try to identify properties. Like if you want to get your picture for the front page of the New York Times of the amygdala lighting up, you really have to do grotesque normalizations between time, subject, machine manufacturer, and so that seems like a really general problem, and maybe it doesn't come up so much in nanomaterials, but it seems to come up in a lot of other areas.
You're absolutely right, and that was the point I was trying to make when I was talking about 21st century science, talking about complex stuff, is that if you look at, say, determining enthalpies of reaction or atomic transition probabilities, those are simple phenomena compared to the body, the environment, and things like that. And my honest feeling as a scientist is that we fool ourselves in thinking that we understand more than we do. And if we just take a little bit more slowly, be honest with ourselves. Other questions? Yes.
You had a really cool diagram of, so it was the nanomaterial, then it was properties under certain circumstances.
Yes.
It was a great diagram. And I just want to go back to a distinction you made before between a measurement and a property. And so you said a measurement is a one-time look at nature. And I just wanted to see methodologically, at what point does a measurement transition to a property?
Okay, this is what I often had in there, but I timed this out to 58 minutes, so I took these out. But here's a measurement of Diego Giacometti by Alberto, and then this is the real guy. Okay, so at what point, and he made, what did he make? 1,300 measurements of Diego. Okay, so you make 1,300 measurements. What point do you have the real guy? Well, the way we do it at NIST is saying that you evaluate data in three ways. One is that, have you demonstrated that you identified all independent variables that matter and demonstrated that you control them? The second way is, do the data follow the known laws of nature? And the third way, which is the less useful way of all, is how do they compare with other measurements that purport to look at the same thing? And it's tough. The most exact collection of data in the world are the fundamental physical constants that this puts together on the CODAT and things like that. And they have very tight uncertainties, and some of them are the 15 significant figures. And if you read your New York Times carefully, in the last couple of years, some measurements of one of the things, I forget which one, I don't know, the moment of the neutron or something like that, outside the uncertainties. So, you know, you never really know 100%. And you just have to hope that you have a theory that explains these things.
So completeness.
Completeness and demonstration of completeness, that you did not use the AJAC as your heat bath, have you really, controlled things? There's another slide I had of, if you look at uncertainties in toxicology measurements, that there's a huge, there's a guy, Harold Krug in Switzerland. I don't know if you know of him, but he's done a study of 5,000, toxicological studies, and he finds none of them to be reliable. They don't say what kind of, nanomaterial they really use. They use concentrations that make no sense. Of course you're going to get lethal dose of 50s out of these things because you're poisoning them. You're not, it's not cause and effect. You've shut out all their oxygen, basically. So there isn't a gold standard answer to that, but as long as you keep that in mind, then you can kind of aim at it. Any other questions? Or? Yeah.
This is just a follow-up of
Yeah.
a kind of thematic thing. When you're getting the distinction between measurement and property, how does variance and invariance play a role in that? I'm getting the sense, and you didn't say this, but the sense that a property is going to be something invariant, where a measurement is one point of view, you could have multiple points of view. How do you see the invariance as playing out with respect to the property measurement?
It's a very interesting question, because when you talk about materials, engineering materials, that a great number of what we might call properties, which are not invariant, they're test dependent. Okay, and so, and like, you don't build an airplane based on the properties of steel. You make it on the basis of the results of a standardized test method, which over time has indicated that there's a correlation with performance. Okay, and so a lot of nanomaterials are going to be that way. You put carbon nanotubes into a tire, do they stay there or not? Do they go into the environment? That's a big question. There's a reason why pilots walk around the plane before it takes off. They're looking for cracks. Why? Because they develop aluminum that will hold together until a crack is visible. And that's not a property. That really is a result of a standardized test that has been correlated with basically wings falling off a plane, over a long period of time. You should feel safer. They did a good job. Anything else? Okay, thank you. And if any of you people are interested in looking at the Uniform Description System version 2, there are going to be two versions of it, two layers of review. So if you're really a zealot, I'll include you on the initial list. But then when I get back, because there are a couple of people who are really delighted in my misspellings and stuff like that, and I correct all that, then be glad to include you on that, and any comments are welcome. Okay, thank you.